ladies and gentlemen, distinguished guests, it's a great pleasure to be here today, and I would like to give my appreciation first to Professor Balarao, who organized this symposium, and Dr. Chandrasekhar, who helped us to overcome all the difficulties on the way here, and of course Professor Yachmi, who made it possible for me to come here. Without him, I probably would not show up here. And I am very grateful that it's not probably my 5th time in India, and every time that I come here, I'm thrilled because notwithstanding all the difficulties, this country is flourishing, is becoming a central piece of our science community worldwide. And not surprisingly, we have accommodated a lot of postdocs and students from Indian universities in Israel and at the Weizmann Institute particularly. And I would like to mention a decision that was made 3 months ago by the Israeli government to accommodate every year 100 postdocs from India and China in Israel, funded by the Israeli government, as an appreciation to the progress between the 2 and 3 countries, and the appreciation of the scientific quality of the students that come from this country. And in fact, I have been lucky to collaborate with few scientists or few students from this country, mostly alumni of Professor Sienna Rao's lab, and we had few collaborative papers, joint papers with Professor Rao, and I wish this collaboration will continue and go on. And in fact, in a few weeks from now, I will get a new student a former student from Sienna Rao's lab, and it's a great pleasure to be able to accommodate students of this high quality in our laboratories. As you know, I come from Weizmann Institute. It's a small institute in a small country. And nevertheless, we are doing quite well in science. And I hope that I will deliver a message of what kind of science we can do, even in small countries, that has an impact on the worldwide scene of science. So with that, let me start to talk about the subject of my talk, inorganic nanotubes and Fullerene-like nanoparticles. This field, and I would be very, very brief because time does not allow to go into details. But in 1991, I spent a few months in Tokyo, and the word of the day was that Ijima discovered carbon nanotubes. And at that time, it came to my mind that it's not possible that nanotubes will be a structure typical to carbon only. And I thought that one would be able to produce nanotubes and fullerenes from inorganic compounds, and I thought my way how to do that. And in fact, it was very easy for me. Once I posed the question properly, it was very easy for me after a few months of thinking to come up with the answer. And the answer is shown actually schematically in this picture. So because I don't see the screen, I will use my pointer here on the screen in order to show you. So this is graphite. Graphite is made of planes of graphene, sp2 bonded carbon atoms. So you have a hexagonal pattern of carbon atoms. Each carbon atom is bonded to 3 neighboring carbon atoms. And it so happens that this layer are staked together by very weak van der Waals forces. So there is a built-in anisotropy in this graphitic structure. And if you look on a nanostructure, graphitic nanostructure, you see that there are abundant of carbon atoms which are on the rim and which are only 2-fold bonded. And consequently, the structure is unstable because this dangling bone destabilizes the planar structure of graphite. Once you realize it, it is immediately occur to your mind that when you bring this structure to the nano dimension, it will spontaneously fold on itself, curl, and form hollow closed structures. Now, hollow closed structures that we know today as carbon nanotubes and carbon fullerenes are not a trivial concept because chemistry chemical bond is not stable beyond 3 angstrom in general. And even weak van der Waals forces, like we have here occurring between the layers, staking of the layers, are not stable beyond 6, 7 angstrom. So what makes hollow structures which are as large as 10 nanometers and beyond in these hollow structures, in these closed-case structures? The answer is that the energy that is lost, or the chemical energy of these structures, when you have nanostructures with so many rim atoms who are only two-fold bonded, makes these structures unstable, and they prefer to close on themselves, annihilate this dangling bond, and form hollow closed structures. With the same concept in mind, one can ask himself why molybdenum disulfide would not do the same. Molybdenum disulfide is also a layered compound made of staking, of van der Waals staking of layers of molybdenum disulfide. Each molybdenum atom is bonded to six neighboring sulfur atoms, and they are staked together via van der Waals forces. Now, if you look on one such layer from the top, from the C-axis, you see that in the bulk, molybdenum, which is central here, is bonded to 6 sulfur atoms in the bulk, but on the rim, it's only 4-fold bonded. And so for sulfur, sulfur in the bulk is bonded to 3 neighboring molybdenum atoms, and on the rim, it's only bonded to 2 molybdenum atoms. So the consequence is that when you bring this structure to the nano dimension, and you have a lot of these rim atoms, the structure will not be stable in the planar form, and instead it will form structures like that. So these structures are actually hollow closed structures of tungsten disulfide and molybdenum disulfide, which we have reported in Nature in 1992 and 1993, and then in Science in 1995, which are formed by simply folding the layers and clothing them into a hollow closed structure. And basically, it's a spherical wall of tungsten disulfide. Each black layer is a tungsten disulfide layer, which is folded one into the other in about 15 layers of subsequent layers. And instead of, if you compare it to C60, which is made of precisely 60 atoms of carbon, this is nothing similar because it is much larger. There are about 300,000 atoms of molybdenum and tungsten in this structure. And there are many defects here, but nonetheless, it's a hollow closed structure. And initially, when we produced it, we produced very few of those, and it was always questioned that I would often get in my lectures, how do you know that this is a distinct phase? In order to prepare a distinct phase, you have to synthesize large amount of this material, purify it, measure the properties, and see that it has distinguished properties from the bulk form. And that indeed what we did. But it took us a few years to realize this goal, because the synthesis of nanostructures is not trivial. This is a high temperature synthesis which goes on at around between 800 to 1,000 degrees. And it's very difficult to control a reaction of that sort with toxic gases and at these temperatures, because diffusion is very fast and growth is very fast. So we had to learn to cheat nature and to do chemical synthesis so that we do arrested growth of nanoparticles which will spontaneously form these structures. Now, once we saw these structures, it immediately occurred to my mind that there should be very interesting applications to these nanostructures. The reason is that these nanostructures reminded me immediately as a nano ball bearing. You have a very stable and flexible and inert structure because the sulfur atom on the rim have very low surface energy, and so they don't tend to bind to the underlying substrate. And therefore, I thought that these nanoballs could serve as perfect spheres between different substrates. I would like to remind you that the Romans 2,000 years ago and beyond used lead balls in order to move stones, big stones, and build large buildings. And so this, in a way, is a concept which goes now to the nanostructures. So we can do the same thing now, but with particles as small as 100 nanometers and below. So with that in mind, we synthesized this material. We went to the laboratory of my colleague and friend, Professor Lev Rapoport from the Holon Institute of Technology in Israel, and we measured the lubrication behavior. So this is a much later picture, but nonetheless, the first paper that we published in Nature in 1997 about the behavior, the lubrication behavior or tribological behavior of these nanoparticles was very important. It's a landmark paper because it shows the way for a progress using nanotechnology. And so we were able to show that by adding these nanoparticles to oils, we could improve the tribological behavior of interfaces dramatically. And this is shown exactly here. So this is a late work with the laboratory of Fabrice Desanoy and Jean-Michel Martin in the École Centrale in Lyon. And unfortunately, my arrow does not come very easily here for some reason. Okay, so this is the friction coefficient as a function of time. And here you see the lubrication with simple oil. Here in this curve, you see the lubrication with molybdenum disulfide particles, macroscopic particles, which in the form of platelets. And here are the fullerenes, the nanoparticles, which we called inorganic fullerene-like structures, or in short, IF. And we could show that they are excellent lubricant. They are much better than any solid lubricant that you know of. And the friction coefficient under extreme condition of 1.4 gigapascal, which is 14 tons on your edge of your nail, is quite surprising to see frictions as small as this. Now, this has been slowly industrialized, and it has been actually a company was a spin-off company was formed in order to exploit the commercialization of these ideas. And indeed, Nanomaterials, which is the present company that exploit this technology, is now has commercialized this product. It is much difficult to produce a lot of kilograms or even tons of these materials on a large scale, but nevertheless, I'll show you in a minute a few pictures from the production facility. So these results were very important in showing that nanotechnology is not just a nickname for nothing, for scientific knowledge only, but it also has a very important technological value. In this work, which came later on, we have been able now to impregnate these nanoparticles into metal coatings. And now, once you do that, you can prepare self-lubricating surfaces. These self-lubricating surfaces has great importance in variety of applications. So in order to, so here you see, first of all, the SEM picture of these nanoparticles impregnated in cobalt metal sheets, film. And here you see a comparative comparison of the friction behavior of the film with few percent of these nanoparticles. The friction coefficient goes on, is very low, below 0.1, and goes on for a long time compared to the uncoated or to the uncoated stainless steel substrate or the stainless steel substrate with a coating of cobalt alone. So you see an advantage, great advantage in impregnating these nanoparticles into this metal coating. This has already been exploited in the industrial products, basically in aerospace products. I won't be able to go into details, but nonetheless, there is a big tendency now to use this technology for other applications, and I'll show you one or two examples of this sort of application. Another very important recent application is in the field of nanocomposite. There is quite an important and extensive effort, mostly in Europe, to exploit these nanoparticles in reinforcing polymer nanocomposite. And I would like to mention especially two laboratories, the laboratory of Hannah Dodiuk in Shenka College in Israel, and the laboratory of Mohammad Nafakh in Madrid. Muhammad did great work in demonstrating that by adding 1 to 2% of these nanoparticles into polymer, variety of polymers, thermoplastic polymers, you can reinforce the structure of polymers dramatically. And there is a lecture this afternoon by Dr. Al-Azhar from the Holon Institute of Technology giving some details on another work on reinforcing polymers with these nanoparticles. So this has an important future, still no product in the field, but getting very close to that. In fact, the reason that these nanoparticles work so well is that because they have advantages as good lubricant, they have advantage in improving the rheological properties of the polymer blend, and they disperse very well. In fact, by combining carbon nanotubes with these nanoparticles, there is a very nice synergistic effect, which has demonstrated by the Muhammad Lafach laboratory. So the nanoparticles, our IF nanoparticles, produce a very good dispersion of the carbon nanotubes in the structure, and you get reinforcement of the polymer, so you get higher strength, higher stiffness, and higher fracture toughness by adding both components in very low quantities. And I won't be able to go into details, but there are a number of articles which are cited here at the bottom. One application that I mentioned, which it should be one slide before, is the medical applications. We have gone quite far with medical applications of these nanoparticles. One would think what kind of medical applications one could think for these materials. Indeed, there are many. I won't be able to describe all of them. A lot of them are now being developed now in progress, like cancer therapy, urological treatment, heart diseases, etc. But the one piece that I can show is for root canal treatment files. We have demonstrated that by coating the files with the cobalt, metallic film of cobalt with the nanoparticles, we can improve dramatically the fatigue resistance of the files, and so they can last for longer period of time, which has a very big advantage in endodontic treatment. To show you a little bit of the production or how we made progress with the production of these nanoparticles, Dr. Al-Azhar in the afternoon will speak about that a little bit more further. I won't be able to go into the details of the synthesis of these materials, but nonetheless, we started with few milligrams of these materials, pure phases, already in '95 by my former student, Dr. Yishai Feldman. Then in the year 2000, we were able to start already the fluidized bed reactor, which produced about 20 grams of Fullerene-like tungsten disulfide nanoparticles. Later on, we could produce few grams of tungsten disulfide nanotubes with the same reactor under somewhat modified condition. And in 2007, company Nanomaterial was already able to produce slowly. They scaled up the production, and they had actually split the production between high-quality Fullerene-like nanoparticles and high-quality nanotubes, as I will elaborate in a minute, and lower-grade, industrial-grade materials, which are now produced in 150 kilograms per day. I wish we could sell 150 kilograms per day, but nonetheless, we have a facility, working facility, for 150 kilograms per day of these nanoparticles, and I think it's quite remarkable that with very modest support and very modest means, we were able to produce at very high temperatures nanoparticles of this sort that are sold worldwide, including in India now, for a variety of applications. With that, I would like to go immediately to the nanotubes, the story of the nanotubes. We observed the nanotube, the tungsten disulfide nanotubes, at the same period of time, or actually in the first paper, the first Nature paper, described the tungsten disulfide nanotubes, again, multi-wall nanotubes. And as you see here, you see a multi-wall, a TM picture of a multi-wall nanotube made of about 10 walls of tungsten disulfide and a hollow core of about 10 nanometers. And we were able to slowly grade up or scale up the production And it took us many, many years. In fact, it took us 90 years to realize the first kilogram of nanotubes, which is shown here. So this is the work of Dr. Alazak, which is present here, and she will describe her work this afternoon. And we were able to synthesize this at 2011, more than 1 kilogram, or few kilograms, in fact, of these nanotubes. And now, actually, we can synthesize about 1 kilogram of pure nanotubes at 1 week of work, or maybe less even. And they are high-quality nanotubes, as you will see in a minute. So not only they are very cheap, other than the energy cost, you pay very little for the raw materials, which we use. We use tungsten oxide and hydrogen sulfide, but we had to spend 19 years in order to learn the growth mechanism. And the applications came, or the proposed applications came quite soon afterwards. So this is a work that has been done recently by Dr. Alazak. I won't show it because Dr. Alazak will probably present it in this afternoon. These are electrospin fibers and PMMA fibers impregnated with the nanotubes, which lead to major reinforcement of these fibers, nanofibers. Let me show you, deliberate in few minutes, about these mechanical properties of these nanotubes and nanoparticles. This is a very beautiful piece of work, and I would like to show you a movie. The reason I show this movie is to show you that once you control the synthesis of the nanoparticle to a great detail, you can get a material that its behavior are predictable from quantum mechanical calculations. And this is very important because most materials, they are dictated, their mechanical properties are dictated by the chemical bond, but also by the defects and grain boundaries and dislocations in the structure of these materials. These nanostructures, these nanotubes, have no defect, or almost no defect, and consequently, their properties are dictated by the strength of the chemical bond between tungsten and sulfur. And this is shown very nicely by this movie. I'll show only 1 or 2 movies of those. So these are 2 movies that were produced. First, I'll show this movie. This is a movie that shows the attraction or the tensile experiment of one single nanotube glued to 2 edges to 2 AFM tips. And this experiment was carried out or was performed by Yifat Kaplan-Ashiri. It is a completely quantitative experiment. It's not just nice picture. So that you really have to exert a lot of power or a lot of force in order to break these nanotubes. And perhaps the most exciting movie is this one, which I'll show. And this is the bending of this nanotube. So these are very, this is a nanotube glue in the edges to 2 AFM tips, and now we push them face to face, and we try to break the nanotube, and it won't break. It's very strong, very flexible. So although the nanotubes are, theoretically, they are not as strong as carbon nanotubes, if you take 1 kilogram of this nanotube, at least 50% of them, or maybe more, will behave the same way. Namely, they will not break even after if you push them at 20 gigapascal force. That means that they can be used to reinforce polymer, and we have also performed beautiful experiments on shock absorbance of these nanotubes. They wouldn't break before 25 gigapascal shock wave applied on them. So this shows the importance of chemistry, or how chemistry influences the electronic properties of this material. Let me go back to my presentation and show you a few more pictures before we go on. So, how much time do I have still? If 5 minutes would be enough. Anyhow, we wanted to measure from fundamental basis the properties of these nanotubes and Fullerene-like nanoparticles. And perhaps I will skip it, but I will just explain this experiment that we did and published last year. So jointly with Professor Wagner from my laboratory, 2 students, Ohad Goldbart and Ofer Tevet, were able to spread single individual nanoparticles on a wedge of silicon wafer and measure the compression strengths and then also the shear strengths of these nanoparticles and how they will break, eventually break under what forces. And indeed, we showed that they can withstand pressure of about 2 to 3 to 5 gigapascal under both loading and shearing before they start to fail. And this is very important for lubrication because that describes actually, this is the first description of rolling friction that exists in nature or in science. So we have demonstrated that these nanoparticles are very robust and at the same time they roll under very high pressure and they can provide very effective means of lubrication under boundary lubrication conditions. And I won't show it for the lack of time. I probably will finish here by showing you 1 or 2 more slides. And this is the rhenium dope. So I told you that we had a very good lubricant, but we had an idea to improve this lubrication behavior even further. In order to achieve that, we learned to synthesize nanoparticles or nanotubes which are doped with rhenium atoms. The reason for doping these rhenium atoms is that rhenium sits to the right of molybdenum and tungsten and consequently has 1 extra electron. When you substitute rhenium into the lattice of the nanoparticles as shown here, so here you see a single rhenium atom in the lattice of the molybdenum disulfide Fullerene-like nanoparticles. This picture was taken by a Titan microscope in the Jülich by Daniel Stropper and Lothar Huben, 2 collaborators from in a joint ERC project. They are in Jülich, in the research center in Jülich. And so we learned how to dope. Each nanoparticle has about 30 to 50 atoms of rhenium. So each nanoparticle basically has about 50 electrons on the surface, and it behaves like a charged colloid. And consequently, these nanoparticles, although they look very similar, they first of all conduct electricity much better, as shown in this graph. So you start from the resistivity versus temperature. You start with the undoped material, and when you heavily doped it, you get a material which is completely conductive at low temperatures. And then when you measure the lubrication behavior, you see that it produces enormously low friction coefficient, below 0.02, close to 0.01 under heavy lubrication, boundary lubrication conditions. This is quite amazing because if you take the undoped material, the friction coefficient is much higher. Also, the wear is very low, and so we can get now new materials, which behave very differently from undoped materials. And in fact, this is the first time that controlled doping can dictate the tribological properties, and we show by this way a relationship between tribological and electronic properties of nanomaterials. These materials have a great future, I believe, but it will take some time before we can synthesize these materials in kilograms and we can achieve industrial products from this. But nonetheless, the future is already there. I think that I'll show you just briefly a few more